People often say that turbulence is the last great unsolved problem in classical physics, but how would we know if we'd ever solved it? In this talk, I want to talk about universality in turbulence, the topic of this conference, and show you how thinking about this question tells us some insight into the different ways of describing turbulent flows. So I'm going to talk about two topics. One is on fluctuations in dissipation, which will be the second part of the talk, and the first part of the talk will be on transitional phenomena, and here are my collaborators and funding sources. So let's begin with some propaganda. So this is from the Feynman Lectures on Physics, and this is shortly after the equations of fluid mechanics have been introduced. The speaker, the writer, is Richard Feynman, who is famous for his work on quantum electrodynamics, which has enabled us to do the most accurate theoretical and experimental measurements ever done in science, and they agree to something like 10 decimal places. And yet, in this part here, Feynman, the master of quantitative physics, if you will, is writing down the equations of water flow. And what he says is that we find a set of concepts and approximations to use to discuss the solutions: vortex streets, turbulent wakes, boundary layers. When we have similar equations in a less familiar situation, and one for which we cannot yet experiment, we try to solve the equations in a primitive, halting, and confused way to try to determine what new qualitative features may come out or what new qualitative forms are a consequence of the equations. And then he talks about the next great era of awakening of human intellect may well produce a method of understanding the qualitative content of equations. Today we cannot. So again, this is somebody who spent their life's work trying to calculate things quantitatively, and here he's talking about the qualitative content of equations. Now, the qualitative behavior of matter is the domain of statistical mechanics, and my goal in this talk is to expose and in our work, is to expose the qualitative content of the equations of fluid mechanics by understanding the phase diagram, the universality, and the scaling laws of turbulence, because in statistical physics, that's what we mean when we understand something qualitatively as well as quantitatively. And the good news is that we've made a start on this, and there are novel predictions and perspectives that arise based on statistical mechanics, both in transitional flows and in what are called fluctuation-dissipation relations, and these theoretical ideas have also been tested experimentally, at least they've begun to be. So the main message of my talk is that there are two types of universality to be thought about in turbulence. So one is the one that most of you are familiar with, the idea of fully developed turbulence having some universal scaling laws like Kolmogorov 41 or multifractal scaling and so on and so forth. The second one is distinct from that, and that is what happens at the laminar turbulent transition, whereas I'm going to show you there's strong evidence that there is a non-equilibrium critical phenomena arising at this point here. So these two things are critical points, two separate critical points with their own scaling laws, crossovers, and universality classes, and in between there are unifying concepts of fluctuation dissipation, rare events, and mean flow interactions, which I won't really have time to go into in this talk, but I'll say something about this at the end. So what does it mean to solve turbulence? Well, if you asked a physicist, what she would say is predict the fluctuations at small scales. And we all know that this is the idea of the Richardson cascade, where you have large eddies that spin off smaller eddies in a Hamiltonian process. And because it's Hamiltonian, it does not involve friction. And from this, you learn that viscosity should not enter into the equations for, say, the energy spectrum. And so what you end up with is Kolmogorov's prediction that there should be an inertial range with a scaling law k to the minus 5/3 with dissipation at large k and the integral scale where energy is fed into the system. And he achieved this prediction by using dimensional analysis to introduce his Kolmogorov scale, which gives you the dissipation, and then two assumptions that it's not just dimensional analysis that gives you k to the 5/3, it's also an assumption about analyticity. And that assumption is that if I take the wave number and system size L, take this limit to infinity, which means looking at small scales, it assumes that there is that this limit is analytic and smooth and regular. It isn't, and that incomplete similarity, as it's known, gives rise to this extra correction to the K41 scaling, which is known as the intermittency exponent. And I'll have something to say about that later. The second answer might be, if you talk to an engineer, the engineer might say you should predict the dissipation experienced at large scales. So this is measured. This is Nicaradz's data from 1933. This is the logarithm of the friction factor, basically the pressure drop per unit length normalized by the kinetic energy. And this is for a pipe as a function of Reynolds number. The pipe has roughness on the walls, and the roughness varies over an order of magnitude, nearly 2 orders of magnitude. For pipes that are smooth, the friction factor comes down here. As the pipes get rougher, the friction increases, of course, and these curves here show the evolution of that. You can see that as a function of Reynolds number, there's a lot of complicated regimes here, which I'll describe in detail, but that's the thing that you would like to be able to understand and is important for applications. Another answer you might have is, well, what you should do is connect the scales. You should predict the dissipation experienced at large scales from the fluctuations at small scales. In other words, does this tell you something about that? And as I'll show at the end, the answer is yes, one can make some steps in that direction, but a lot more needs to be done, and that is a frontier that we're actively pursuing. Another answer to the question is to say, well, perhaps we could predict how and when fluids become turbulent, and is there some universality at this transition? And the answer to that is yes, there's been an enormous amount of progress made in the last 10 years by people who are here in the audience, Dwight Barclay, Björn Hoff will be here later on, and others. So let me talk about that now. So the original experiments were done in the 1880s by Reynolds, and what he did was he took a pipe, he injected ink in order to visualize the flow, and what he found is that as he increases the flow speed, the flow goes from being smooth, regular, and laminar, as shown here, to being jagged, irregular, and turbulent down here. But in the middle, there is this transitional region where what he called flashes of turbulence arise, interspersed by regions of laminar flow. Today, we call those things puffs, and what I want to do now is show you what we've learned about puffs. So the question you might want to ask then is how much turbulence is in the pipe? Here, there's none. Here, there's a lot, going to 1. And then in the middle here, something is happening, and I'll show you later experiments which have actually measured this with great accuracy. So this transition is not spatially uniform. You get rare, sharp bursts of turbulence, and that's what makes it difficult. And so we have to understand what is a quantitative description of this transition. Another connection is this, that turbulence resembles phase transitions. So if you look at this one here, the turbulence fraction as a function of Reynolds number is going up continuously, as far as we can measure, from 0, reminiscent of a continuous phase transition. And here, the energy spectrum, which is the velocity order correlation function, basically is parallel correlated, again, reminiscent of what you get in a second order phase transition. So there's a lot of connections there, and those connections are of course, not accidental. Today, this is how the transition to turbulence is studied experimentally. These are brilliant experiments done by Björn Hoff, starting in 2008 in their most recent form. And the question is this. Take a flow, which is laminar, in a pipe. The flow is believed to be stable, linearly stable to arbitrarily high Reynolds number. But then you perturb it, and once you perturb it, that creates turbulence. How much turbulence it creates depends on what the Reynolds number is. But the experiment that Björn did was to disturb the flow and then create a puff and ask whether the puff survives as it gets to the end of the pipe or whether it dies along the way. So the idea is we're looking in a regime where turbulence is not yet stable, and then as the turbulence propagates, it kind of dissipates and dies away, and we want to measure what its lifetime is. But the way that he did this was to do this experiment in a carefully controlled way, and you'll hear about it later in this workshop, do many repetitions, measure the survival probability as a function of Reynolds number and time. And when you do that, what you find is this phase diagram. This is the Reynolds number as shown along here, and then what are plotted on these graphs is the probability of survival as a function of Reynolds number and time. These are numerical simulations from one of these papers. And the color tells you the turbulence intensity. So what you're looking at there is a single puff, and in this regime, it is metastable. It is going to eventually die away. If you look at the logarithm of the probability of survival as a function of time, you see that it decays exponentially, and the slope of the exponent depends on the Reynolds number, and so it has this memoryless form as shown here. If you plot that lifetime as a function of Reynolds number, you get these data shown up here. But this is the logarithm of the puff lifetime. And so the fact that it's upwardly curving shows you that the puff lifetime is increasing faster than exponential with Reynolds number. When you go to higher Reynolds numbers, roughly in this regime here, the puffs don't just decay, now they start to split, and then these puffs become independent and also can either decay or split as they will. And in that regime, one also finds that the splitting probability, the time between splitting events, follows a curve like this. As you go to higher and higher Reynolds numbers, turbulence is more and more favored. So therefore, as you go to lower and lower Reynolds numbers, it's reasonable to expect that the splitting time will increase as you go down in Reynolds number, and that's what it does, again with an upward curvature, suggesting that the lifetime is scaling faster than exponential. If you take a double logarithm of these data, you see that they fall on a nice straight line with an intersection which is identified as the critical transition for Reynolds, the critical Reynolds number for the transition to turbulence. Why should this double log be meaningful? Well, I'll show you later on that there is a theoretical reasons why this double exponential form should be understandable. Okay, so now I want to talk about how one goes about making a theory for this. And to start off with, I want to compare this with what happens in physical systems like condensed matter physical systems like magnetic systems. So what you do there is you do this. You start off at your lowest level of description, which is, say, the electronic structure. But that's much too hard, so then you look at the magnetic moments of the electrons, and you form a model of the interacting moments. And that model is called the Ising model, and it is in principle a quantum model. But that quantum model is also too hard to solve, so you just wave your hands and say, let's make it classical, and that model is also too hard to solve, unless you're in 2 dimensions. There's no external magnetic field, and your name is Onsager. In that case, this model is exactly solvable, but otherwise not. This model then, the next step is to say, well, let's look at the symmetries of this model. So when you look at the symmetries of this model and write down an effective free energy for the system, what you get is a description called Landau theory. And from Landau theory, you can then use a renormalization group theory to calculate the universality class of the transition. So what this looks like is the following. This is the magnetization as a function of temperature, and as you can see below a critical temperature, it rises continuously from 0, and it does so with a critical exponent beta. If you sit on the magnetic temperature field plane, you sit just exactly at Tc, and then ask what happens if you apply an external magnetic field to the system. That would normally be expected to cause the magnetization to increase linearly proportional to the applied field. But at a critical point, linear response theory breaks down, and you get a new scaling law, and both of those scaling laws can be encapsulated into what's called a data collapse formula like this. The important point is that in the vicinity of the transition, to make Landau theory, what you have to look for are weak, because the magnetization is small, long wavelength modes. Those are the ones that drive the instabilities, the infrared divergences and so on, that give rise to non-trivial critical exponents that you would not be able to get from mean field theory. So now we turn to turbulence. Well, the analog of the electronic structure is the kinetic theory, the lowest level of description. There's a coarse-grained description, which is, of course, the Navier-Stokes equations. And so what we should be thinking about then is what is the analog of Landau theory, and then what is the analog of the renormalization group universality class. So how can we make a start on this? So what we did is we tried to identify what are the long wavelength collective modes at the laminar turbulence transition. And we don't know how to do this in any systematic way, so we just did direct numerical simulations. And the idea was to take a turbulent puff, put it in a very small box so we could kind of just keep that puff there, and then try to look at what are the fluctuations that go on inside that puff. To cut a long story short, what we found is that near the transition, there are 2 modes that are important. One is the turbulence itself on small scales. The other is an azimuthal mode whose radial dependence is shown here, which is essentially long wavelength. In the simulations, we identified as the k = 0 component, but in reality, it's a long wavelength component. But the important point is that that zonal flow, as it is known, has an oscillatory relationship with the turbulence when the energy of the two modes are plotted as a function of time. What's happening there is that the turbulence is in fact inducing this mode, this zonal flow mode, because the anisotropy in the turbulence is driving flow that starts to circulate around. But the circulating around flow, the zonal flow, then shears the turbulence and makes it more isotropic. And so that then suppresses the Reynolds stress, and because the turbulence has been suppressed, then the zonal flow itself has been suppressed, and so therefore now the turbulence can rise again. And so you get the sequence of oscillations which are reminiscent of activator-inhibitor oscillations, or if you like, prey and predator oscillations in an ecosystem. And by this, what I mean is the following. If I have a prey, let's say sheep, and I have a predator such as wolf, the presence of the prey causes food for the wolves, so their population goes up. But then, because of their population goes up, they eat the sheep, so the prey population goes down. Now the wolves have got no food, so they starve, and then the prey population can go back up again. Just the same thing that we saw in turbulence. So what we're saying then is that these things are very related. So let's think how we would model a predator-prey system if we took seriously the idea that this was the sort of Landau description of the system. So the way we model predator-prey ecosystems is by looking at what happens at the individual level of description. So we're statistical mechanicians. So for us, what that means is if I tell you what the behavior is of individuals in an ecosystem, let's say predators and prey, what happens is we write down the two-body interactions between them, and then we use statistical mechanics to work out what happens at the large scales for the population. So here, for example, A means predator, B means prey. So this means that the prey plus the energy, the food, or which in this case it comes from the laminar flow, the shear, prey plus food produces enough energy that the prey is able to reproduce, and you get two prey. Here is another one. A predator runs into a prey, and with probability P, eats it, and then gets enough energy for the predator to be able to reproduce and produce two predators. And so we can take a sequence of reactions like that and simulate those, or even do analytical calculations to try to describe what happens to the system at the population level. So just to go back then, we have a mapping between the zonal flow, which is the predator, the turbulence, which is the prey, and the vacuum or the empty site, which is the food, which is the shear energy from the laminar flow. The Navier-Stokes equations are quadratically nonlinear, so that means that every vertex of interactions between these modes is going to look something like these diagrams here. So this one here says the zonal flow meets turbulence and then annihilates the turbulence and produces more zonal flow. And that corresponds to A plus B goes to A plus A in the predator-prey dictionary. So now let's do this. Let's take this predator-prey Landau theory of the transition, and let's now simulate that or understand it in detail, and I'm going to show you that its phase diagram, its lifetime statistics, and the universality class of the transition come out of this and agree with the data. Okay, so this is the diagram that I already showed you. This is the phase diagram for pipe flow turbulence. For the predator-prey model, the analog of the Reynolds number could be either the predation rate or it can be the prey birth rate. Because if the prey birth rate is very slow, like once every century, then the wolves will eat all the sheep and they'll just die away. If, on the other hand, the prey birth rate is fast, let's say once every second, well, then the wolves will not be able to eat fast enough to eat all the sheep, and so the populations will coexist. And so as a function of this parameter, it turns out you get a regime where the ecosystem collapses, a regime where a puff, meaning a prey and predator as a spatial blob, will eventually decay, a regime where the prey and predator will coexist and produce traveling waves, which are like the splitting puffs, and then finally a regime where you get an expanding population, a so-called slug. If you take this model and just look at the statistics for the puff splitting events, don't focus too much for now on the precise structure of these curves. This is from pipe flow turbulence. This is the population splitting in the predator-prey ecosystem, where a pattern-forming instability of the predator-prey blob causes there to be these puff splitting events. Then you get a similar type of phase diagram. And now if you measure the statistics of the extinction time when you're in this regime, and the statistics of the time between population splitting events when you're in this regime, what you end up with are curves that look like this. So this is the turbulence data that I already showed you, and this is what you get from the predator-prey Landau theory description, which never even saw Navier-Stokes equations, but reproduces the same phenomenology. So the extinction in ecology is basically the death of turbulence. Now what we'd like to understand is the universality class of the transition, and what I've shown you already is that near the transition, turbulence is like a two-fluid model with two modes being predator-prey modes. What I'm going to show you now is that this universality class is actually directed percolation, and to get there from here, we have to do more statistical mechanics, statistical field theory, to take this model and show it predicts what a universality class of directed percolation. I'm not going to go through any of the technology for this. I'm just going to show you this in a graphical way. Now, back in the 1980s, Yves Pommeau speculated that the transition to turbulence might be in the universality class of directed percolation, and he did that because he said turbulent regions can spontaneously relaminarize, go into an absorbing state, but they can also diffuse the turbulence and contaminate their neighbors. So one plus one dimensional directed percolation is the following game. This is time, and this is space. These are occupied sites, and there are links between the sites with probability p, that's the percolation probability. If this site is occupied, then at the next time step with probability p, you can get to this site. With probability p, you can get to this site, to this one, but there's no bond from here, and so the percolation process stops here. If you think about it carefully, you can see that each of these steps from time to time plus one follows these basic processes. Annihilation, filled site goes to an empty site. Decoagulation, a filled site goes to two filled sites at the next time step. Diffusion, hopping diagonally. And coagulation, two filled sites going to one filled site at the next time step. So that's directed percolation. And when you vary the percolation probability, what you find is that for small p, the flow cannot get through to the other side. For large p, the flow, you can always find a percolating path through the system. And at the critical point, the flow actually gets through to the other side. And if you measure how many occupied sites there are at large time, what you find is that that number goes continuously from 0 with an exponent beta. And there's other things to say about the critical behavior here, but I don't have time to go into them. So what's happening is if you think about a puff decaying in 3 dimensions from the directed percolation picture, that would be directed percolation in 3 space and 1 time dimension, as shown here. In 1 dimension, this corresponds to a region of occupied sites, and then as the last pixel disappears, the pixel showing you the turbulence, that corresponds to the longest trajectory in this 1 plus 1 dimensional directed percolation. So what that says is that the longest path tells you the lifetime of this turbulent puff. And this longest path then is given by extreme value statistics. In other words, if I assume that these sites are all independent, what is the longest path? What is the maximum length for these random percolating paths? And in extreme value statistics, what one finds out is that the probability for the maximum of a bunch of random numbers obeys 3 distributions, the Fisher-Tippett distributions, of which one, the most common one, is the double exponential form. And that fundamentally is the reason for the super exponential behavior, although there's a lot more to say about it than that. If we take our predator-prey model and write it down now in space, so I and j now represent site labels, this thing here is not an expectation value, it just means nearest neighbor, then what you find is you get a set of reactions that look like this. Near the transition to the prey extinction, the prey population is small and no predator can survive, so then you take those terms away, and now you're left with just a two-trophic level ecosystem model. And if I look at these different terms here and write them down graphically, you see that those graphical terms represent exactly the four basic diagrams of directed percolation. So near the extinction transition, the stochastic predator-prey dynamics reduces to directed percolation. And this has been tested experimentally, and you'll hear more about this from Björn Hoff later on in the workshop in a very quasi-one-dimensional Couette flow, where you can visualize the turbulence in successive rotations of a flow in a Couette system. The blue here represents the turbulence states, the yellow represents the lamina, and these are experimental data which look like directed percolation, and quantitatively they fit directed percolation as well. And there's other tests that Björn will no doubt go into. Here is another test. This is in 2+1 dimensions. This is in Walef flow, in a planar shear flow, and these are beautiful simulations done by Chantry et al. And again, they were able to determine the critical behavior near the transition, measure the universal scaling function, and other things like this. As for the predator-prey modes, those have also been seen, not in this system, but it's hard to see them in the pipe flow, but in tokamak, they've been observed. They were predicted long ago by Pat Diamond and collaborators, and were observed about 10 years or so ago in a tokamak in this paper here. Okay, so what I've shown you is that we have transition to turbulence has a critical point, which is seems to be in the directed percolation universality class. So now I want to switch gears and talk about fluctuations and dissipation. I showed you at the beginning some data from Nikaradze. So these data were taken in a pipe flow, but what was different was that he glued sand grains onto the sides of the pipe, and he measured the pressure drop per unit length normalized by rho u squared, or if you like, normalized by the Reynolds number squared. This is the curve I showed you already, and let me quickly walk you through these different regimes. So this is the rough pipes. These are smooth pipes. This regime here has a slope of -1. This is because the friction factor is the pressure drop per unit length normalized by the Reynolds number squared. So that would normally be going as the velocity or the Reynolds number itself, but by squaring, it goes down as 1 over Reynolds number. Then there's a transition to turbulence, which is what I've been talking about up to now. And then there's this regime here called the Blasius regime, where, as you can see, as the pipe gets smoother and smoother, the friction factor goes further and further down this line with a slope of Reynolds to the -1/4. And you'll hear much more about that from Björn Hoff, hopefully, later this week. And then at large Reynolds numbers, the flow friction factor becomes independent of Reynolds number, and then just depends on the roughness, and it scales like the roughness to the 1/3 power. That's called the Strickler regime. So what is the origin of these scaling laws? Well, I want to tell you about another feature of universality that occurs at phase transitions, and that is the idea of data collapse. Now, I talked about power laws before, but this is the thing that I haven't told you about. Ostensibly, the magnetization of a material depends on its temperature and its applied field. But as I showed you on a previous graph, the theory predicts that if you scale temperature in a particular way depending on the field, and you scale the magnetization in a particular way depending on the field and temperature, then all data from different magnetic materials falls onto one universal curve as shown here. And the solid line that goes through these data is the prediction from renormalization group theory with no adjustable parameters. Now, when we talk about turbulence and critical phenomena, I'm now talking about turbulence beyond the critical regime. We know that in general at high Reynolds numbers we have energy spectrum going as k to the 5/3, which is reminiscent of the correlations in critical phenomena going as, say, k to the -2 in mean field theory. I just showed you the large-scale thermodynamics, the magnetization of the system obeys data collapse as well as these power law scalings. So my question is, what is the analog of data collapse for turbulence? So to cut a long story short, what happens is you can show that by doing sort of Kazanov type scaling arguments, you can show, or at least argue, that if there is a critical point at a large Reynolds number controlling the flow, then this should be the data collapse form. And here are Nicaragua's data in the turbulent regime plotted in this way, showing you that the data indeed do collapse with an intermittency exponent, which is consistent with spectral estimates. So there is an analog to the data collapse from large-scale thermodynamics. This is truly amazing. What it says is, by simply measuring the pressure drop across a pipe, Nicaragua's measured the anomalous spectral exponents, the intermittency exponent, 8 years before Kolmogorov even wrote down the mean field theory. And therefore, this friction factor scaling tells you about the intermittency corrections to velocity fluctuations. So this spectral limp is an example of a fluctuation-dissipation relation. You can see explicitly that macroscopic flow phenomena reflect the nature of the turbulent state. And this is shown here. This is a dissipation. This is the friction factor. Again, I'm not going to go through the arguments. They're in these papers here, which show you that heuristically, at least, the friction factor is related to the energy spectrum through this relation here. And that gives you the scaling laws, the Strickler and Blasius scaling laws. Now, in 2 dimensions, you have 2 cascades, not just the inverse energy cascade, but also the forward entropy cascade, and that has a different exponent. So that says then that the friction factor in 2-dimensional turbulence should scale differently depending on whether you have an entropy cascade or whether you have an inverse cascade. And so we tested that experimentally. So what we did was we made a soap film system here, a gravity-driven flow. We use laser Doppler velocimetry to image the velocity profile and measure the wall stress. And we did this in 2 different geometries. One geometry was where we had a grid generating the turbulence, and that gave us a forward entropy cascade of k to the minus 3. The other geometry was no grid, but one wall being rough, and that gave us an inverse energy cascade, or at least a power and energy spectrum consistent with a k to the minus 5/3. And then when we plot the friction factor measured in these 2 different flows with different energy spectrums, what you can see very clearly is that the friction factor scaling with Reynolds number is 1/4 in the case of the energy cascade, the inverse cascade, and 1/2 in the case of the entropy cascade, the forward entropy cascade. This shows you quite dramatically that there is a connection between the velocity fluctuations at small scales and the drag experienced at large scales. So now I want to end by just talking a bit about some ongoing work. So I talked about puff decay at Reynolds numbers around about 2040. At higher Reynolds numbers, what happens is the turbulence actually spreads and fills the pipe, and that's called a slug regime. And that's a regime that we can also access by these simple universal models. So this is a shout out to Dwight Barkley, who will be talking later today. He has pioneered a beautiful description of turbulent puffs and slugs, focusing not on the single puff, but on the interactions between them, and they interact through the mean shear flow field that is really driving the turbulence. And he'll tell you more about this, but the work works by making an analogy to excitable media. The work that I showed you about is just focused on looking at a single puff in isolation and trying to understand what is the critical behavior inside the puff, but the single puff spatial extent is not taken into account there. The laminar shear flow that drives it was not included up to now. So now what happens if we include the mean shear? So this is what happens. So this is the description and very consistent with data from Björn Hoff, showing you that you get different regimes of puffs, splitting, and then slugs, which are called weak slugs and strong slugs. The same thing happens here in these predator-prey models of the energy budget. And so what we can see is that we get equivalent predictions in terms of the phase diagram and the kinematics of puffs and slugs. So this is what I've told you. I've told you that the transition to turbulence is a non-equilibrium phase transition in the universality class of directed percolation. So we've now got a lot of evidence for this assertion coming from theory, coming from experiments and numerical simulations. And then I've showed you that the friction factor also tells you that there's a connection between large-scale and small-scale structure by both the data collapse and the way that the friction factor depends on the nature of the small-scale velocity fluctuations. So I'll leave you with the references, and I'll be happy to take any questions.
A few questions. Yes. Hi. How do I press the white button?
Big black button.
And then it'll light up.
In these directed percolation models, slightly modified, allow for the possibility of a discontinuous transition as well. And there I guess there's the analog of a tricritical point taking you from one to the other.
Right.
Is there any possibility for looking for that in your systems?
Well, we could look for that, but it hasn't been done. I mean, there's different models of directed percolation. Most of the models are actually in this the regular directed percolation universality class. You can get models like the Domani-Kinzel automaton, where you can get a whole phase diagram of different directed percolation exponents.
I think a very small modification of the standard DP allows this possibility as well. So
Right.
Somewhere in your parameter space.
We haven't really addressed that. I mean, the evidence, as far as we can tell, both experimentally and from direct numerical simulations, is that it really is a continuous transition. And actually, maybe Bjorn will talk about some joint work that we've been doing about that. Did you have a follow-up question, or are you done?
I have a small other question, which is that experimentally one can probe this as a 1D or a 2D transition. I noticed you had some 2D. I guess there is no possibility of studying it as in the fully 3D context, or is there? Because it looks to me like you seem to need at least one confined direction to make this analogy with DP really clean.
I wouldn't say that the restriction is because of that. I mean, it's simply to visualize the flow, and I don't think anybody thinks that this is a low-dimensional claim.
No, but there is a difference, which is that the 3D case, you have long-range hydrodynamics kicking in a way that doesn't if you have even one dimension.
Well, I would say it's like this, that if you look in the Koretz flow and you look in pipe flow, there are three-dimensional modes going on. I mean, for example, I showed you an azimuthal mode in this way. If you look in the Koretz flow, there's a zonal flow going in this direction and this flow radially. So these flows, even though we represent them as 2D, are really intrinsically 3D.
Okay, we can talk more.
Yeah.
So my question was maybe related. Have the zonal flows been measured in experiment?
No, they're very weak. They're very weak to see. But you do see flows that may be like zonal flows in channel flow. So if you look at this is work from Grégoire Lemoux and Eduardo Resfried. So when you look at the if you look at the turbulent patches in channel flow, you also get large-scale circulations that develop around them. And actually, it's something that we've talked about, trying to actually quantify that and see if they would be the analogs of this. But they're weak modes to see. And so we've talked about with collaborators about trying to see them experimentally, but I think it would be hard to do.
The comment is they have been measured in plasma experiments.
They have, as I said, as I showed you the data. Right. Estrada et al. They've been able to measure them there. It took a long time. It took 20 years to measure them in the MHD. So in non-MHD physics, they've not yet been measured. So, but yeah, that's why I showed you the Estrada et al. Data.
Okay, last question.
I'd like to hear your opinion about locality. In phase transitions, in conformal bootstrap, the main point is that there is a local conformal theory. Conformal means local scale transformations. And that is why the statistical systems are so easy to characterize. So, in my view, in the case of turbulence, there is ascension on locality, especially because of incompressibility, and BOSOR just describes how vorticity fields everywhere influence velocity, and also displayed itself in the growing correlations of velocity. What do you think about that?
I think in the transition to turbulence, it's not so important. And the reason is because what we're looking at these puffs, which are emergent structures, and we can measure the forces between them. They're not long-range forces. So the incompressibility is for the whole velocity field as a whole. When you break it down into the components, it doesn't really apply. And so we actually, maybe Bjorn will talk about this. We've actually measured the forces between these puffs and confirmed that they're short they're short range. So now at the infinite Reynolds number end, that's still an open question.
Okay, I suggest we continue this interesting discussion during lunch, maybe, and then let's thank the speaker.
What I'm going to talk about now will be turbulence, string theory, and Ising model. It's slightly more precise than turbulence topology and Ising model. So how these subjects are related? It's a long story. It started in the late 80s and early 90s when I was studying turbulence in Princeton, and I published 2 papers which nobody understood except Srini, who kept trying to verify or disprove my statements, and finally there were very interesting results supporting part of my statements, and then I came back to physics and started developing it further and found out that I left very important aspects undeveloped, and those I developed already in NYU. So there is a dual view on the fluid dynamics, geometry versus field. So Lagrange and Helmholtz and Kelvin and Arnold represent a geometric view. And Euler, Navier, Stokes, and Kolmogorov were developing the field view. And that was very successful until recently intermittency was found. And intermittency is very difficult to explain without specific geometric view on vortex structures. So there are 2 approaches to that problem. One of these approaches is kind of phenomenological approach. You could derive from Euler or Navier-Stokes equations, you could derive the exact equation for the loop average, and then this is loop, this is circulation. I'm sorry, this is, I don't see it. Do you see it? Okay. It's better to use the pointer sometimes. Oh, I see. So this is circulation around the loop, studied by many, many people, theoretically. There is a Helmholtz theory, and there is a Helmholtz evolution equation. Derivative of circulation is related to integral of product of velocity times vorticity plus the viscous term, which will drop because we're interested in fully developed turbulence in the inertial range where that is unimportant. So we are going to consider large circulations, much larger than viscosity, and also consider large loops. So what can be found in that region? The object which we are going to study will be something like Wilson loop in gauge theory, which I also studied at my time in the 80s and developed some loop equations there. And similar equations can be written, except they're simpler, can be written for loop averages in the fluid dynamics. It's exponential of some phase factor proportional to gamma with viscosity playing the role of Planck's constant. And probability, of course, is related by Fourier transform to this wave function. And this and averaging goes over time in presence of Gaussian random forces at large scales. So we don't need to specify the large, the random forces because we are studying the universal aspects. So as a function of time and a function of the loop, this object satisfies the loop equation, which was first written down in this work of myself, in 93, and then I studied it this year already. During that year, I found some more solutions. So the equation has the shape, form of the Schrödinger equation, with viscosity playing the role of time, and then there is some specific Hamiltonian, which is like, so this area derivative, which I'm not going to describe, some mathematical notion which is analogous to the coordinates derivative in ordinary Hamiltonian. So this Hamiltonian is some very sophisticated kinetic energy term, quadratic in this array derivatives. What the main observation which was made back in the early 90s is that this equation with small viscosity here allows for the WKB asymptotics. In general, for arbitrary viscosity, that is like Schrödinger equation, and in the low viscosity and large gamma limit, it has WKB asymptotics, which is dramatically simpler. You have to solve some nonlinear classical equation. And that nonlinear equation is sort of instanton from the point of view of this known analogy that, intermittency, the tails of the distribution, are related to instantons of some field theory which describes it. In this case, these are non-local field theory given by this Hamiltonian, and you have to find those instantons which will describe to you the tail of PDF. Now, the advantage of the loop equation, that's a closed functional equation for observable quantity with clear geometric meaning. You have to study function of one variable instead of three. And this advantage is that we have to learn quite sophisticated mathematics, more than sophisticated than Fourier analysis, and have to learn to write equations with equal, proportional, and instead of just approximately and sort of equals. And that is an effort. I'm not saying that I know that sophisticated math. I had to learn it, and I'm inviting everybody to follow that example. And there are people who helped me with that. So the tails of the PDF at large gamma are determined by the WKB asymptotics, which was suggested to be of this form. Logarithm of PDF is proportional to some power of gamma times some negative power of area. And area is area inside the minimal surface bounded by the loop. And beautiful work by Srini and Kartik Iyer showed that indeed that's the case. There is exponential law. Srini will talk about that later today. There is a very universal exponential relation between, for PDF, over 8 decades. And PDF is basically exponential, but at closer look, it's not exactly exponential because this index mu is equals 0.82. And alpha was measured to be equal to 0.55. And Kolmogorov scaling would correspond to 2/3, which is ruled out in that measurement. And in other words, that is already intermittency. The tails of PDF are already intermittency phenomenon. But the intermittency in terms of circulation is very simple phenomenon. Some classical solution, simple exponential. Everything simplifies for circulation with a good reason.
Sorry. Could you explain what R and eta is?
Huh?
What R and eta is? Could you explain what that is in your previous slide?
Hold on. So there is two indices, mu and alpha.
What's R?
The R is the size of the loop. Okay. It's a square of size R. And eta is what is eta? It is a smaller scale of a viscous scale. Yeah, viscous scale corresponding to the flow. So basically, you would want Reynolds number to be larger, and they did measure larger Reynolds numbers, but I'm just showing the one for smaller one. I'm not responsible for this data. But those data inspired me to study the microscopic theory of this phenomenon. So the first result, which I obtained this year in the beginning, that indeed in my theory alpha should be exactly 1/2. It's very strange that you could derive something exact from loop equations, but that's what followed from those loop equations. Alpha is 1/2. Now, well, 0.55 is not quite 1/2, it's different, right? So if you look at the data for the moments of the circulation, these moments are described by area to some power, which is called lambda of p in this notation, because a to 1/2 is r, so it's r to lambda of p. And lambda of p should be asymptotically equal to 2p times alpha. And I claim that alpha equals 1/2. So this is, again, the data from that work of Srini and Kartik. And you see that that is lambda of p divided by p as a function of p. So for p equals 3, it's exactly Kolmogorov. Kolmogorov is 1.3. It's not constant at all. It is going down. And I fitted that data from 3 to 10 by a very simple formula, 2p alpha plus 0.9 log p. That's a subleading correction. It perfectly fits the data, and that gives a different value. Alpha equals 0.5 over 6. So in this lambda of p over p asymptotically approaches 1, but it's a slow approach. It tends to 1, and I'm claiming it will go the remaining way from 1.1 to 1, but it will do it slowly. It is a very interesting problem to actually see what happens at larger moments and larger Reynolds number, and I'm eagerly awaiting those experiments. But at least I see that those recent measurements don't contradict my prediction of alpha equals 1/2. There is another exciting prediction of this theory. Namely, if you study the mean vorticity in presence of large circulation, my result from the loop equations is this vorticity is directed towards local normal plane, local normal vector of the minimal surface. So if you have the minimal surface, for example, square, then normal vector is z, proportional of orthogonal direction, and therefore there will be mean vorticity directed in z direction, which is kind of obvious, but still people were surprised when this was indeed checked. This is a result of the paper which Kartik and Srini will publish later, and this shows exactly this thing, average value of vorticity along the perimeter, for each point at perimeter of square, and it only captures direction of that vector, not the constant. So unit vector cosine of the direction of vorticity with the z direction. So it's practically 1. So there is a very strong indication that indeed vorticity is directed where loop equations wanted to do. Now, here is what I would predict for the more complex case. I call it soccer gates. There are two squares attached at the corner, and that's a solved film which I computed in Mathematica on that loop. So it's not flat anymore. So the local normal vector to that thing is different. It's different from here to here to here. It's not constant. So that will be very non-trivial prediction. It's easily measurable. Just a matter of waiting for those supercomputers queues to process, because that's like riding a bus in Moscow, which I did 30 years ago. It's very slow. Supercomputers are a shame. I do faster computations faster on my laptop. So anyway, it's still in the queue. I don't know whether that will be confirmed. I'm sure it will, but I don't know whether it is. Now I would like to spend a few minutes on a microscopic theory, and I'm not going to describe it all. I'm just going to tell you most important things. And the most important thing is that turbulence is statistics of vortex cells. You know, back in the 90s, I had to convince, and I was shouting in a desert, but nobody listened. But then it was basically evolved. Now it's a commonplace. We saw these vortex cells today, in particular in the talk by Irwan, and every talk showed those pictures, so I don't need to sell it anymore. So that was my initial assumption in the 90s, but then lately I found that there is something very interesting on the surface of these vortex cells, and that's the only thing which I'll have time to describe. I call it Klepp's string. And then there is another ingredient which describes these vortex cells as Ising model. Spin 1 is the cell inside of the cell, and spin -1 is outside of the cell. So the most important thing is the following thing. There is a Liouville equation which tells us that stationary distribution for any Hamiltonian system, and Lagrange motion of the fluid is Hamiltonian system, must commute with Hamiltonian. But it's not exponential minus beta h. So that's some other conserved, symmetric, invariant object which is sitting here but is not equal to Hamiltonian, because Hamiltonian doesn't describe it. So something fell here. I don't know what to do with that. I'll just hold it. Subtract that from my time. That's not my fault. So there is simple observation that vorticity is not uniformly distributed, but rather has fractal dimension equals to 2 plus 1/3. That's a simple dimensional estimate of from the Biot-Savart formula. If the domain here has fractal dimension df, then this can be estimated as r to the df minus 2, and we know it is r 1/3, so df equals 2 plus 1/3. But that's less than 3, meaning that vorticity doesn't occupy the whole space, and everybody knows that today. So I'm not going to sell it. Now, of course, Lagrange coordinates are driven by the same velocity, and I'll skip the mathematics, but I will tell you most important things. There are only two, if you are considering invariants which are conserved in Hamiltonian sense and also parametrically invariant, there are only two. One is the volume of each cell. It is conserved. This thing here is parametrically invariant, and it is conserved by Liouville equation because the volume element is conserved. So that's one object which could sit in exponential. Sorry. So you could place net volume of vortex cells in exponential. But of course, there is also vorticity, and vorticity is well, here is the thing. Turned out there is no bulk conserved things which will describe vorticity. All integrals of vorticity, they exist in even dimensions, but in odd dimensions where we live, there is no such thing. It will be integral d volume of square root of determinant of vorticity, exists in 2, exists in 4, equals 0 and 3. Of course, helicity wouldn't work because it's pseudoscalar. It's not positive. Now, if you look further and make the long story short, then there is a Klepp's field, so-called Klepp's field, which I prefer to describe as a complex variable, and vorticity is described as by this formula, and you could, there is U1 symmetry. You could change the phase of the Klepp's field, and the most important thing is this: in order for the vorticity not to leak out of the vortex cell, the normal vorticity to the boundary at every point of that vortex cell should be 0. And that means that there's only one U1 invariant solution for that, and that is that Klepp's field have absolute value equal constant on the surface of the cell. It could have a dynamic phase, but the value, absolute value is constant. Then indeed there is no flow of vorticity outside. Therefore, the rest is remarkable. The rest is topology. In these conditions, the integral around every loop which is contractible on the surface of the cell is 0. Integral over every loop which goes around the handle is conserved. It's topological invariant, so-called winding number. But what is most interesting is that this theory is known. It was solved before. It's called bosonic string theory. It's called compactification of bosonic string from U1 to from U1, which is the circle, to the surface, which has some number of handles. And this corresponding partition function was exactly computed in the 80s. And that directly applies to this case. There are no continuous variables left, only discrete variables, so-called moduli and winding numbers, and that's it. So that is the partition function of this theory at fixed shape of the cell. Now, the remaining thing is that I'm not going to describe this mathematics because that is not the most important. The most important thing which is left is that the dynamics of the shapes of the cell is described by Ising model. Ising model, if you look at that from the point of view of random phases, exactly describes all possible configurations of one phase inside another. And summing over all spins of the Ising effectively is equivalent to the summing over all self-avoiding surfaces on the boundary between these phases. So what I'm adding here is on the boundary between these phases, there is Clebsch string sitting. So everything is in principle calculable. This is what I suggest as a Landau theory or universality class for this fully developed turbulence. Thank you.
We'll just take one quick question. Should we give
Go
it a
ahead.
chance? Yes.
Yeah.
What from the Navier equation enters in the area law?
Use your C mic, please.
Excuse me?
That's the black. That's the black. Yeah.
I can answer. I understood your question. So,
Okay, understood. Because you seem to be only using the.
well, in inertial range, I don't need Navier-Stokes. Navier-Stokes is like a boundary condition for dissipation at small scales. So when and in this case also, when I'm talking about the vortices structures, they have some thickness, and that thickness is actually of viscous scale. So the way the area law follows from this microscopic picture is very simple. Here is this loop of the shape of the sucker gates, and then there is some blob, like vorticity pancake, which is forced to stretch inside, and because they are entered with exponential of minus volume, the classical configuration is correspond to minimal volume. Minimal volume at fixed width is minimal area. So that's how vorticity enters the game. I mean, viscosity.
Okay, I think we better get to the next speaker. Let's thank
Hello, everybody. This is a joint work which is done together with Enrico Fonda, Dimitri Krasnov, Ambrish Pandey, Sandeep Pandey, and Katapali Srinivasan. The motivation for this work comes from solar convection. The convection in the sun is taking place in the outer shell of the sun, and we know that it is organized in a hierarchy of large-scale patterns which can be probed at different scales, starting from granulation via supergranulation all the way up to giant cells, which basically fill the whole convection zone. Let me point you to two properties of solar convection, which we are specifically interested in. The first one is the very extremely small molecular Prandtl number. The Prandtl number compares the viscosity of the fluid to the diffusivity of the temperature field. It's almost across the whole zone, 10 to minus 6, and then it grows towards the surface to values of 10 to minus 3, extremely small, as you can see. And that is mostly due to the strong radiative transport of the energy across the convection layer. The second property is related to the characteristic velocity in units of the speed of sound. And you see that compressibility becomes very important close to the surface, but over a significant fraction of the convection zone, the characteristic velocity is relatively small compared to the speed of sound. And these two aspects suggest that at least some details, some issues in relation to the formation of patterns and in relation to understanding their interaction with the small-scale turbulence, we might discuss in the context of Rayleigh-Bénard convection, which is a much more simplified convective flow, which we are going to study in the following. So here we have an Rayleigh-Bénard convection flow in a large aspect ratio system, 25 times 25 in units of the height of the layer at a rather small Prandtl number. You see two snapshots in this simulation, a view from the top onto the streamlines, and here this is the midplane of the temperature field at the same instance. And when you are applying a time average over a certain time window, you recognize patterns which are reminiscent to those which we know from the onset of convection, these typical rose structures, and here these ridges. And it's exactly these structures and their slow evolution which we are going to be interested in the following. We are currently pushing these simulations to Prandtl numbers which are much smaller than those that can be obtained in laboratory experiments. This is a simulation at a Prandtl number of 10 to minus 3, which require large computing resources because the turbulence, the fluid turbulence, is highly inertial in such systems. Here you see the vertical velocity in the midplane. Red is upwelling fluid, blue is downwelling fluid. And here is a magnification into a small area. This is basically an aspect ratio 1 cell, and I have indicated the thermal boundary layer thickness, the thickness of the temperature boundary layer, which is about 1,000 times thicker than that of the viscous of the velocity field. That means basically these boundary layers are decoupled of each other, and that should have some impact on the dynamics across the whole convection layer. And that's what we are interested in. We have conducted a whole series of these simulations where we basically picked two fixed Rayleigh numbers at 10 to 5 and 10 to 6. And we varied the Prandtl numbers across 4 orders of magnitude, all the way down to 10 to minus 3. And as you can see in this picture, where we are quantifying the turbulent heat transfer across the layer, the heat transfer becomes increasingly inefficient when we are going to the very low Prandtl numbers, reaching almost the diffusive limit at the smallest Prandtl number value. And the reason is we have this very blurry temperature field, which you see here due to the extremely high diffusivity. And that makes it different to pile up gradients for the temperature field. And also the convective heat flux is significantly reduced, as you can see here. The story is exactly in the opposite, goes in exactly in the opposite direction if you look at the momentum transfer, which can be quantified by a Reynolds number, which is defined here. It becomes a better and better situation if you decrease the Prandtl number. The Reynolds number grows. You can also see this here by the root mean square fluctuation profile across the convection layers. Nevertheless, if you apply a time average over your velocity field, you recapture again this very regular roll patterns, even though the turbulence is already highly inertial in those kind of systems. We are currently extending these kind of simulations by introducing a temperature dependence of the thermal diffusivity. In that way, we are able to manage exactly the Prandtl number profile, which I have shown you on my first slide. And the system becomes now immediately non-Busy-Nest. That means we are breaking the up-down symmetry in our convection flow. And what you can see here are the mean temperature profiles for 3 cases. There's the one case with this prescribed temperature dependence. And there are 2 reference cases which correspond to the Rayleigh-Bénard system which would be present at the bottom and to the Rayleigh-Bénard system which would be present at the top. One is a very low Prandtl number system, which you can see here. And the other one is a very high Prandtl number system, which you can see here. And you see that the temperature patterns in our flow with the temperature dependent diffusivity has basically ingredients of both of these flows, these strong ridge-like structures which you can observe here, and this fine filamentation which is coming from the low Prandtl number aspect. Furthermore, we see that we have here in this system some kind of beginning hierarchy of structures which reach into different depths of this highly stratified system. If you look at this temperature profile, you can imagine that this requires a tremendous effort of computational power to resolve these extremely thin boundary layers. So how can machine learning techniques help us to understand the large-scale dynamics, the evolution of the convection flow at the largest scales, and the contributions to the turbulent transport? And we have approached this topic from different directions, applying unsupervised or supervised machine learning techniques. And the unsupervised part, for instance, was done in the Lagrangian frame of reference by looking at trajectory clusters, which we have obtained from the Lagrangian description of these convection flows, or by applying a Koopman eigenfunction analysis on the basis of diffusion maps. I'm going to spend the rest of my talk with these 2 approaches of supervised machine learning. The first is basically that we are applying these methods to learn the structures as they evolve in the turbulent flow. And for the second part, we are actually trying to set up a model that is able to predict the dynamics in these flows. So what are we doing? Well, we have to perform a tremendous data reduction in this approach, starting from the full 3-dimensional snapshots via temporal or spatial averaging, which reveals these coarse-grained large-scale patterns in our system. And then we apply neural networks to even further reduce this information in view to the transport. What is given here in black are exactly those regions in which we have an enhanced convective heat flux in our system. How are we doing this? Well, we are applying special neural networks which have a U-shape. The one half of the U is typically that what you apply for each classification network. And what you would end up is a local classification if the data belong to the set you want to describe or not. But then you have to compose it again to this pattern of ridges. And for that task, you need this expansion path, which is given here on the right-hand side of this slide and forms this whole U-shaped network. And so what we have done with this technique, which is basically applying the neural network as a classical image segmentation tool, a very sophisticated one, is we have looked at the slow dynamics of this network, which can be characterized by by annihilation and a reappearance of these defect points. And we can basically follow this evolution over a few hundred convective time units. It's a very slow, gradual evolution. We have also quantified the heat transfer which goes across this particular structure, and we have found that it remains a contributor to the turbulent heat transfer, although these patterns, as you can imagine, will change with increasing Rayleigh number. Let me come finally to the second part of this supervised machine learning branch. Here we have been started recently to really predict the turbulent convection dynamics, and to keep it simple, in a first step, we went to two-dimensional turbulence data at a rather high Rayleigh number, 10 to 7 Prandtl 7. So that's a fully developed turbulent convection flow already. In a large aspect ratio, you have this cellular structure. And the idea is to come up with an equation-free and fully data-driven reduced order model to describe the large-scale dynamics. So you have to introduce some kind of memory in your network architecture, which can be done by these recurrent neural networks. There are a few of them, and what we have been chosen is the so-called reservoir computing model, which is also known as liquid Boltzmann machine or echo state network. So what is the idea of such a reservoir computing model? You have an input layer and you have an output layer, and in a convolution network you would have a bunch of hidden layers which are closely connected to each other by convolution operations. This is substituted in our case by a so-called reservoir, which is nothing else but a sparse random matrix on which you have this very simple dynamical system dynamics, which is nonlinear, because here's a tangent hyperbolicus, which takes the role of this neuron activation, and then you are basically run this dynamics on the reservoir. The reservoir computing model has a big advantage because the optimization is done only with respect to the output layer. So in contrast to many of the other deep learning algorithms, we don't have to perform the backpropagation, which typically is costly and very expensive. So, and then you are running this whole machinery as an dynamical system, and you predict the dynamics. So you cannot feed in your turbulence data blindly into such a network. You have to perform, again, a data reduction step. There's no chance to do it without it. And what we have chosen is a very standard way. There's nothing fancy about it. It's just a POD mode dynamics, which we have performed to our convection flow. And then we truncate this expansion. And then we say, okay, what we want to learn is the 150 most energetic degrees of freedom of our dynamical system, which represent the large-scale structure of the flow. And I give you here two coefficients and their time evolution. It's mode number 1 and it's mode number 50. This is the training phase. And then we are going into the prediction phase, and then clearly the blue and the red curve, which stands for the training data, and the one which are predicted by the model deviate of each other. But nevertheless, the model is able, the reservoir computing model is able to predict some kind of dynamics which comes close to what we would like to see in such a reduced order model. And this can be shown here by comparing directly the simulation snapshots, the POD modes, and here the corresponding projections with respect to our reservoir computing model for temperature and the two velocity components. Also, the statistical information is not too bad. This is the mean temperature profile. More interesting is the convective heat flux across the layer, where we have to compare POD model and reservoir computing model, or the temperature fluctuations across the layer. So at the moment, we are intensively working on studying the dependencies on all these parameters which you have as the sparsity, the spectral radius of the reservoir, etc., etc. Okay, that's all I wanted to say. Here's the summary. We have looked at turbulent superstructures in the turbulent convection flow at very low Prandtl number, and we think that is an interesting testing bed to study the small-scale turbulence and to come up with some parameterizations of the unresolved scales that go beyond Prandtl's mixing length theory, which is still the workhorse in stellar convection or in stellar turbulence. And 2 ways to basically study the large-scale dynamics in such flows. The evolution of the patterns have been suggested by these deep convolutional neural networks and by this reservoir computing models. These are the references and the funding agencies, and thank you for your attention.
Time for just one quick question. Yes.
So very interesting. On the last part, when you did the POD for the initial dimension reduction, are you doing that over some finite time window? Because if you waited long enough, your POD modes would just be sines and cosines in X.
Yes.
Okay.
Okay, I think that should wrap up our morning session. We'll be back in this room at 2. There's a poster session. There's some structure.
At 2 o'clock, we'll all line up here.
Then I think lunch is served, right? Lunch is outside. Thank you.